So you've seen a little bit now of how to use hashing. So you've seen it in writing your own hash code method, having that method be used to organize elements into a hash set, and also using your own key and value pairs using a hash map. So now hopefully you have an understanding of almost like a client view of using hash tables. And so now we're going to kind of get behind the scenes a little bit, and we're going to think about more of an implementation view. So we're going to actually think about building our own hash table to see how things work behind the scenes. Now, just like we did for list, we're not making our own hash tables and studying this because this is something you'll probably do. Most likely outside of this class, you're going to use HashSet or HashMap or one of the other hash-related classes in the Java Standard Library or some other external library. But it's important to understand what's going on behind the scenes. And so that's why we're going to kind of take some time to look at the nitty-gritty details of how things work, how things are happening behind the scenes, and also write some of that code ourselves. So let's start out with kind of the heart of hashing, which is the hash function. So that hash function, again, is the method that determines the location or the index of a value based on the key. So it's you take the key, you give it to the hash function, and it spits out some index. Okay, so hashing is the process of using that hash function. A hash function has one input, the key, and one output, that location, that index. So let's go back and think about in the first video, we talked about a very bad hash function. So if you recall, we were having a hash table of voter data, and we said the key was their phone number. So the key is their phone number, the value is the voter object, and we said that the hash function was we just take that key, the phone number, and we just look at the last digit, and that's the location. Okay. Now, why is this a bad hash function? Well, it's a bad hash function because there are a lot of different phone numbers that are going to have that same digit, right? There are tons of phone numbers that end in 0 or end in 1 or end in 2. So this isn't a very good way to go from key to index, right? Because we are going to have a lot of keys that map to the same index. And remember, we talked about when implementing your hash code method that in general, although it's allowed to have two unequal objects have the same hash code, we want to avoid it as much as we can because it'll make things more efficient. So this hash function we have here of just using the last digit is not avoiding it at all, right? We basically only have, 10 unique values, and all the phone numbers are going to map to those 10 values. So that's a very bad function. But let's think about if we could make it a little bit better. So in thinking about making it a little bit better, let's actually go a step further to start with, and let's make it perfect. So a perfect hash function would have one unique address for every single key. So one unique index for every key. If this were the case, we would absolutely be doing our best to strive for that two equal objects have the same hash code and the reverse. Two objects with the same hash code will also be equal because we're saying every object has its own unique hash code. So this is what's known as a perfect hash function. So let's take a look at what that would look like for our voter example. So perhaps for our voter example, we would just use the whole phone number, right? So the hash of the key is just going to be the key itself. The hash of the phone number is just the phone number. So the 7 digits of the phone number will define the 7 digits of the location. Okay, now this is true that it's perfect hash function because each number will link to only one unique position. And no two phone numbers will have the same position. So that's great. That means each phone number can be used as a key to exactly locate one voter. That's great. However, because there are 7 digits in a phone number, and we're only talking about not even the area code, we now need almost 10 million spaces in our table, even if we only have, say, 5,000 data on 5,000 voters. Okay, so we have to have a ton of slots in order to support this perfect hash function, even if the amount of data is much, much less than that. So this creates what's called a sparse situation or sparsity. So a hash table is sparse if their space to hold data is much, much greater than how much data is in there. And much, much greater is a bit subjective, but a lot of times people will use kind of the square root of n as a general guide. So if you think about the last slide we looked at, we had 10 million. If you take the square root of that, if there's less data than that, that would be sparse. And that's certainly going to apply to the example we just looked at. That's not a hard and fast rule, but it's just kind of a good guideline. Okay. So although that perfect hash function is good because it allows different objects to always be mapped to different hash codes, it's not ideal because it leads to a very sparse table. So how can we revise that? Well, let's see if we can think about a way to compress that range of values into a smaller size, right? So instead of needing almost 10 million values, can we think of a way to compress those to get it closer to the number of locations we really want to use? Well, one way to do that is to take that key and use the modulus operator. Modulus, remember, is remainder. So if we take the key, so let's say we are using again the phone number, and we hash it to the phone number like we just did, but then we take the modulus of the table size, well, this is going to take a whole lot of numbers and condense them down to a smaller set. So make sure you understand how the modulus operator works. Let's say, just as a very simple example, you're talking about a table of size 3, and you have a bunch of keys, let's say numbered from 0 to 20. Well, 0 mod 3 is going to be 0, 1 mod 3 is 1, and 2 mod 3 is 2. Now we wrap back around. 3 mod 3 is 0, 4 mod 3 is 1, and 5 mod 3 is 2. So using a mod 3 allows you to take any number of numbers and map them onto 3 numbers. It's going to map every number onto either 0, 1, or 2. So when we think about this in terms of hashing, saying modulus table size is going to take any number that we're given here, and it's going to map it onto one of this many numbers. If our table size is 100, it's going to map it onto 100 numbers. If our table size is 1,000, it's going to map it onto 1,000 numbers. So it's going to compress our 10 million possible key values into, let's say, 1,000. Make sure you understand how this is working. So you have to really understand how the modulus operator works, and then make sure you also understand how it's working in this context of thinking about converting the key into a location. So let's keep going with our voter example. Let's say we do have data only on 500 voters. We could maybe make our table size 1,000, even double, right? That would still be not very sparse. It would give us a little room. Okay, so now let's say, again, our hash function's the entire phone number. So the hash of the phone is just the phone, but then we're going to take a modulus of the table size. So now we have our phone number of 5551234. The hash of that is the phone number. And then we take mod 1,000. And we're going to just get the number 234. So that's going to be our location. We take the number, the key, 5557890. We hash that to the last 4 digits. Sorry, that should be actually hashing to the whole. This is a typo down here. I'll fix that. Anyhow, this is going to hash, right? If we take it to mod 1,000, it's going to hash to 890. Okay? So now we need a much smaller table, only size 1,000. That's very good. But you might be thinking, there might be a problem here. Well, let's look at 2 phone numbers, 5556234. If we take that mod 1,000, it's going to hash to location 234. And 5551234, we take that mod 1,000, that is also going to hash to location 234. So now we have 2 numbers that get hashed to the same location. So that's a problem. Which number do we put there, and where does the other one go? Right? So the whole idea of us trying to improve our hash function was to reduce all those numbers having the same index, right? When we were just indexing from 0 to 9, basically. So we've solved that problem, but we solved that problem first by going to a perfect hash function, but that was too big. So we've kind of shrunk it down to now having 1,000 options. That seems like a good balance, but we still have this possibility that 2 unequal objects are going to have the same location. So how do we handle that? Well, when that happens, it's called a collision, and it's not unexpected. And there are 2 main ways to address it. One is called open addressing, and one is called separate chaining. So let's first talk about open addressing. Before we do, let's just keep in the back of our minds what we've said about good hash functions. So good hash functions minimize collisions. We said that when we were talking about the hash code method, right? We said that we want to strive towards having unequal objects have different hash codes. That means we're minimizing collisions, because when two unequal objects have the same hash code, that's a collision. So we want to minimize that. We can't necessarily eliminate it, right? To do that, we'd need a hugely sparse table most likely, but we can try to minimize it. We also want to minimize clustering, which we'll see in a moment when we look at open addressing. We want to try to distribute uniformly across the table. So this is related to that clustering we'll talk about in a minute. We also want to create a table that isn't too sparse, right? So we don't want a hugely oversized table. But of course, we also need our function to be fast to compute. So remember why we're doing this, right? We're creating a hash table so that we can be super efficient in retrieving objects. So if our hash function is some super complex thing that takes a long time to compute, we're losing all the benefit of using hashing. So these are the things we want to keep in mind when we're thinking about our hash functions. Okay, so let's go back to talking about collisions. We've got this problem, right? We have two unequal objects that hash to the same location. What do we do? So the first approach is to use what's called open addressing. And how this works is that when that collision occurs, you just simply use another location. This approach is also called closed buckets, and it's called that because each location or bucket can only store one value. So the idea is once you put a value in that bucket, it's closed. You can't put anything else in there. Okay, so this is called open addressing or closed buckets. A little confusing because of the open closed, but that's just how it's referred to. So I just said kind of vaguely you use another location. So your main question should be, okay, what location? How do I pick that other location? The whole point of the hash was to give me this location. How do I just pick another one? Well, there are a lot of different ways. The one we're going to talk about is called linear probing, but the textbook also mentions some others, such as there's quadratic programming, there's double hashing. There are many other ways of choosing that next location in an open addressing approach. We're not going to cover those other ways. For those of you interested, again, in kind of diving deeper into those details, I encourage you to do so, but it's not going to be something we're going to talk about. So we're just going to look at one method, and we're going to choose the method of linear probing. So this is how it works to use linear probing to add to a hash table. So when we have a collision, what we do is we probe until we find another open location in the hash table, and that's where we can put our value. And one way to do that probing is linear programming. Linear probing, sorry. What that means is if our location is K, but we try to go and put our object in K and K is full, that bucket's closed, we just look at the next location, K plus 1. If that's full, we look at the next location, K plus 2. And so on until we find an empty spot. That first empty spot we find, that's where we put our value. So we basically just go to the location defined by our hash function, and then we just, if it's full, we just keep going one over until we find an empty spot, and that's where we put it. If for some reason in this probing we reach our end of our hash table, remember we're thinking about our table just like an array. If we reach the end, we can circle back to the beginning and keep looking for that open spot. If we get all the way back to where we started without finding an open space, that just means our table's full. We don't have room for another addition, and we can either reject that addition or we'd have to create a new larger table, and of course then we'd have to do what's called rehashing our keys, right? Because remember that our keys are indexed to a location based on that mod table size. So if we're creating a larger table, we're going to have a new table size, so we're going to have to rehash everything. We're not going to really talk about rehashing, but that's another area you can kind of delve a little deeper into on your own. So we're going to look at an example of adding with linear probing in a moment. Before we do so, let's just talk about what happens if we go to retrieve from a hash table. Well, like we normally would with any hash table, we take the key, put it through our hash function to get the location. We go to that location, and hey, if the key is there, hey, we're all done, great. But if there's a different key there, we're not done. We have to keep looking, right? Because it's possible that previously that object was added at a different location. So if a different key is there, we have to keep looking in the next spot and the next one and the next one, and we keep going until either we find what we're looking for, we find the right key, or we hit an empty spot, which means, okay, key must not be there, or we loop back around to where we started. That means the key is not there and our table is full. So let's look at an example of what this would look like. So we're again going to use our voter data. The key is going to be just the last 4 digits of the phone number, and just to keep the display a little bit simpler. And the location of our objects is going to be that key mod the table size. We're going to use a table size of 101. This again is a prime number. So this is another example of using prime numbers in this whole hashing process. Particularly good to use a prime number for your table size. And one of the external resources I've shared with you kind of talks about that a little bit. And you can also kind of again look into that on your own if you want to. But if not, just know that that's a good rule of thumb, is to use a prime number for your table sizes. So again, our table size is going to be 101. The hash of our phone number key is going to be the last 4 digits. And the location is going to be those last 4 digits mod the table size. Okay? So we get in here. And let's say we first want it, this is our hash table. I'm not showing all 101 spots. I've got this just to kind of be a placeholder. And right now everything's null. I don't have anything in the table. Now let's say we want to add a voter whose phone number is 5551214. Well, the hash of that phone number is the last four digits, 1214. If we take modulus of 101, we get 2. So in order to add this voter to the table, we go to location 2. 2 is empty, so we can store the voter and the key there at position 2. So the key is 1214, and our value is just that whole voter object with that phone number, a name, address, all that other information. So we've got one person, one voter in our hash table. Let's add another one. Now let's say we want to add a voter with phone number 5552022. We apply the hash, which gives us the 2022. We take the mod table size, and that's going to give us 2. So we go to position 2, but 2 is occupied. So we're going to use linear probing. So we just look at 2 plus 1. We just go and look at 3. 3 is empty. So that's where we're going to put our key and value. Key is 2022, and the value is our whole voter object. So now we have 2 elements in our table. Let's go put another one in. So now let's say we have a voter with number 5553033. Apply the hash, we get the last 4 digits. Modulus the table size, we get the value of 3. So this voter belongs at position 3. So we go to position 3, but whoop, it's occupied. We're using linear probing, so we just go to position 4. That's empty, so that's where we can put our key and value. Let's add one more, 5552026. We apply the hash, we get the last 4. Take the mod table size, we get the position of 6. We go to 6, and it's empty, so we just put the key and value there. So this is what our hash table would look like after adding those 4 particular voters. Now, how would it look if we tried to get information out of our table? So let's say we now want to retrieve a voter with a phone number 5553333. So, oops, that should be 3033. Sorry about that. 3033. Okay, so again, how this works is when you want to get something out of a hash table, you need the key. So I'm saying, okay, I want the information, all the voter information about the voter with phone number 5553033. So what do? Well, I first have to hash that key. I'll hash that key, I'll get 3033. Then I take the mod table size and I get location 3. So I get location 3. I go to that location. I check the key. Does it match the key I'm looking for? 3033. It does. So there we go. I've found my voter object. Okay, we check 3. It's occupied. It has the right key. Oops. Let me back up there. I looked at the wrong index in my table here. Okay, apologize for that. Let's try this again. Again, pretend this is 3033. Okay, so we find the location, get the hash, 3033, mod 101, and that gives us a 3. So what we need to do now is we look in location 3. We check location 3, and it is occupied. There's something there. But is it the key we're looking for? It's not. It's the key for 2022, and we're looking for 3033. So because we're using linear probing, we continue our retrieval in the same way we continued our addition. We just move one step up. We look at 4. Does that have the key we want? Yes, it does, 3033. So now we've found our voter object. This example is exactly why when you're using linear probing in this way, really any kind of probing, you need to store the key along with the data. You need to do that because when you find a value at a particular location, you need to check to make sure it's the value you really want. And the way you do that is by comparing the keys. Okay, so if we didn't have the key here, we'd look at this voter and we wouldn't maybe know how to tell if it's what we're looking for or not. We have to store the key as part of that information so that we can compare. All right, so let's now retrieve the data for the voter with the phone number 5552023. So first we take the hash, that gives us the last 4 digits, 2023. We mod 101 and we get a 3. So we check location 3. There's something there, but does it have the key we want? No, we're looking for 2023. Okay, so now we check location 3. Sorry, that's the wrong one. So now we move up one space to position 4. We check there. Is that occupied? Does it have the key we want? No, that's got the key 3033. So we just keep checking. So we check 5. Is it there? No, it's empty. So now we say, okay, this voter must not be in the table. There's no voter for that matched key. All right, let's retrieve the data for this voter here, 5552127. And of course, I should note this is a very simplified example that assumes that everybody's first 3 digits of their phone number is the same, right? If that wasn't the case, you would have to make the key kind of the whole phone number, and then you could still take the modulus. But if you had different first 3 digits, those keys wouldn't be unique, right? Okay, anyhow, so we're going to find the location, take our 2127, mod 101, we get a 6. We check location 6. There's something there, but it's not the one we're looking for. And so we'd go on to the next one, 7, nothing there, it's empty, so we know that our key is not in the table. Okay? Okay, what happens now if we remove the key associated with voter 1214? So let's say, where's 1214? Yeah, right here, 1214, formerly in position 2. So let's say that, that voter moves out of town, moves to a different state. We don't want to keep information about them anymore. So we just remove them, right? So now in the table at position 2, it's a null. Okay, no problem, right? However, let's look for another retrieval. So we've removed that voter. Now we're looking for the voter of this phone number of 2022. So let's start with finding the location. Take our hash of the phone, 2022. We take the mod 101. We find position 2. We go to position 2, and it's empty. So we'll say, yeah, okay, it's empty. Our value must not be in the table. There's no matching key. But you and I can see that there is a matching key. It's right here. Okay? The data is there, but we don't find it. So that's a big problem. And the solution to that is with this kind of probing, you have to have more than 3 states. You can't just have empty and full. You have to have occupied, which means there's a voter there, empty or null, which means nothing's ever been stored there, but you have to also have this third state that we're going to call available. And that's what you use when an item was once there, but it has been removed. And the reason we need to keep track of that is because if you're looking for an item and you hit an available state, that means you got to keep looking because the item you're looking for could still be, in a further probe sequence. So if this were to happen, if we were, let's update our table when we removed that voter of 1214, instead of this being null, it would just be available. And so now when we search for 2022, we again do our hash, we get position 2, we see it's available. Available means, hey, at one point there was a voter here. So if that's the case, that means that my 2022 voter could have got pushed further along. So I need to keep looking. So I can go to number 3, and that in fact is where I'll find my object. Okay, so it's really critical with this open addressing that you got to use those 3 states. You can't just have a voter or null. You got to have a voter, an empty or a null, and then this available. Okay, and how you'd actually do that in a programming sense is a bit beyond what we're going to talk about, but just make sure that conceptually you understand why that's needed and also how that trace would look like when you delete things, it becomes unavailable, and when you're trying to find a value, if you hit an available, it means you got to keep looking. If you hit a null, then you're in fact done. That means if you hit a null, your value was not in the table. So the other method of, remember that we're doing this probing because of collisions. The other method we can use to address collisions is called separate chaining. Separate chaining is also called open buckets. Again, confusing because the last one was closed buckets, open addressing. This is separate chaining, open buckets. Again, it's called open buckets because we can think about those locations of the hash table as being a bucket. But in this case, even if there's an element in the bucket, you can still put more in. So that's what makes it an open bucket. Okay. How we use this method is we link values together that all belong to the same hash index using linked nodes. So once we have one element at a certain hash index, if we get another object coming in with that same hash index, we just put it on the chain. We just link them up with linked nodes. Now, we wouldn't use an array, right? Because we don't know in advance how many values we're going to have linked up there. This is kind of a perfect use for linked nodes because we can just add one on when we need it. We don't have to ahead of time say how big that collection is going to be. Okay. Now, separate chaining is a more efficient way to handle collisions, but it also requires more memory space than open addressing. But these days, we usually care more about time efficiency than space efficiency. So in general, separate chaining is used more often. And you can kind of read about how Java behind the scenes hash table Implementations have kind of evolved over the years. There have been some changes to increase and improve efficiency. So you're welcome again to kind of go a little deeper on your own if you want to read a little bit more about that. But just know that separate chaining is in reality what's used more often than open addressing. So let's take a quick look at an example of this. So with separate chaining, when we add a value, we get the location, and if there's already something in that bucket, we just add the value to the linked chain. Now you might think, where do we add it, right? We can add it at the beginning, we could add it at the middle somewhere, or we could add it at the end. Well, it depends what your data looks like. So if the elements in your hash table are unsorted and might contain duplicates, right? So they're not meant to be in any sort of order, and there might be more duplicates, there might be more than one, version of an object, then we should just use insert head. And the reason for that is that we know that inserting into the front of a linked list is the most efficient way. And if our data is unsorted and might contain duplicates, then we just might as well pick the most efficient way. We don't have to look through that list. It's not necessary. So let's just insert right at the head. Now, if our elements are still unsorted, so we don't care about their order, but they're unique, that means we don't want to add a duplicate copy to the hash table, then we should use insert tail. And the reason for that is because in order to make sure we're not adding a duplicate, we have to traverse through that existing chain to make sure there isn't a duplicate. And if we get all the way to the end and we haven't found a duplicate, then we can add that value. Now, if your elements are sorted, then you just have to make that insertion you have to put it in the middle wherever it belongs based on sorted order. Okay. Make sure you understand kind of why we add to different places of that chained list, depending on what the nature of the data is. So let's go back to our voter example, same setup with the keys and the hash function and the table size. So this is what our table is going to look like. Let's first add that. We're going to add the same numbers. We're going to add that 5551214. We get a hash index of 2. We go to 2. It's empty, so we put the data right there. Let's add somebody else, 2022. We get the index of 2. We go to 2, and it's occupied, so what we do is we just link this up next in line. Okay, so now at index 2, we have a linked list basically of size 2. 2 voters in a chain. Let's add somebody else. We're going to add the 3033. That hashes to position 3. We go to 3. It's empty. So we put it there. We get our 2026, position 6. It's empty. We go to 6 and it's there. If we were to get another phone number that hashes to index 6, we would put it right here. And if we were to get another, we'd put it right here, and so on and so forth. So you're just linking together any of those objects that have the same location. Now, what if we want to retrieve? Well, if we want to retrieve, again, this should be 3033. The phone number of 5033, we look up that location, and it's a 3. We check. Our key is there. No problem. Now, if we want to find 2022, we get the location. It's 2. We go to 2, and that first value in our chain is not a match. So we just keep traversing the chain. Check the next one. Oh, next one is a match. There we go. But if there were more to check, we would just keep going down that chain to check. But again, you can see how even with the separate chaining, you obviously want to be striving to have an efficient hash function because you want to eliminate collisions no matter how you're dealing with collisions. You want to minimize them. You want to eliminate as many as you can because anytime there's a collision, when you go to retrieve something, it's going to mean more searching. In the open addressing format, it's going to mean that probing way of searching. In the separate chained approach, it's going to mean potentially looking through a linked chain of nodes. But either way, it's going to involve more searching than just getting the first element you find. So that's why we want to pick a hash function that's ideally going to minimize how many collisions we're going to have. And again, most likely we can't eliminate them because that would require a huge table, but we can try to be thoughtful and try to minimize them as much we can. Okay, so let's take a look at the examples of actually kind of writing our own little hash table and using that open addressing. We're going to look at kind of using open addressing with linear probing, and we'll also look at a trace of that and look at a trace of separate chaining. Before we do that, one last note is that I realized before I said the word clustering, and I didn't come back to talk about that. So clustering is related to this idea of collisions. And basically, if we think about the collisions we had with our open addressing state here. So this is what we had when we had all, we have 3 voters in there. But there we go. Here we go. All 4 voters in the table. So let's look at this table here. We have 4 voters in the table, but they're kind of all sort of on top of each other, right? And the reason for that is because these 2 voters had the same hash index, and then these 2 voters had the same hash index. And so that leads to values kind of all bunched up together, right? Because the 2 came in here, but then the next one with a 2 got moved to 3. So then the one with a 3 had to get moved to 4, and so on and so forth. So collisions and clustering are kind of related. If you have a lot of collisions, that will most likely also lead to a lot of clustering. Of course, you can have clustering without collisions, right, just by the nature of your hash function. But the idea is it's better, especially if you're using, well, if you're using open addressing, you don't want to have that clustering because it just increases the number of extra probes you have to do. Whereas if your data is more spread out across the table, when you do a probe, maybe you only have to move 1 more space to find your object or 2 more spaces. If they're all clustered together, that's going to increase the number of extra searches you have to do. And again, that's what we're trying to reduce because the whole purpose of using these hash tables is to get that quick retrieval. All right, so let's take a look at kind of a behind the scenes code example.